Okay, so now let's welcome our second speaker, Maggie Miller. She's now working at the University of Texas at Austin. And before that, you were also a clay, well, right now you are a clay research fellow as well. And before that, you're working on, for postdoc at MIT, then Stanford, right? And then you graduate PhD from Princeton, if I understand correctly. Focusing on low-dimensional topology, especially cipher surface, if I understand correctly. And then right now, we welcome Maggie Miller for her talk on branch coverings for non-compact manifolds. Let's welcome her.
Thank you. Okay, yeah, thank you also for having me. I also haven't been to Thailand before, so I was very excited to come. Texas is exactly on the opposite side of the world. It's a 12-hour time difference, so I had to choose if I was going to fly, east over Europe or west over the Pacific. My main collaborator's in Korea. I went east over Europe, and he was very personally offended. I've been hearing about that. So, let's see, how does turn this on? Got it. Okay, I usually study four-dimensional manifolds. I'm doing the opposite of that today. I hope that's cool. I'm going to tell you about branch coverings in really low dimensions of non-compact manifolds. So let me start off by actually asking, I know that it's a mix of faculty and students. Who's a student? Like, raise your hand if you're, no, not you. Is everybody, you can't all not be students. Somebody's a student? No? Really? Pudipong is lying. Are you a student? PhD or undergrad or what? Master's student? How's it going? I'm just trying to check, do you know what the fundamental group is? What's the situation? Yeah. I need to know. Okay, that's good. Okay, so let me tell you, if you're a faculty member, I think you have seen covering maps, covering spaces. Maybe it's been a while if you don't do topology specifically. If you're a student, you might not have covered it yet. But this is one of the main topics that you would cover in a course on algebraic topology. It's also one of the main topics that students in my university cover in a graduate course on algebra when they do Galois theory. So it's a really important construction in topology. So this is a map between spaces. I'm going to focus on manifolds, spaces that locally look like Euclidean space. I'm not going to define it because there will be so many examples in the talk. And a covering map is a map that looks like this, where when I look at the target space, if I take any point in the image, it has some neighborhood around it. Here I highlighted it in purple, where when I look at the pre-image, well, all of the pre-image components are just copies of that neighborhood, and they all map homeomorphically down to cover the neighborhood down here. So we usually, again, in my algebraic topology class, call this something like a stack of pancakes. And then here's the actual definition. For any point, you can find a neighborhood, so that in the pre-image, it's just a bunch of components that map homeomorphically down. Great, so that's a covering map. Covering maps are really special. They are classified by different subgroups of the fundamental group of our target space. So there's a lot of rigid structure here. If you pick an arbitrary topological space, you can count how many different subgroups there are. So for example, the two-sphere, which is going to be the main manifold that we look at for this talk, is the only, its fundamental group is trivial, so it only has one subgroup. So here's the two-sphere. It's simply connected, so one subgroup, and that means that it has one connected covering space, which is itself. So this map here is supposed to be the identity map from the two-sphere to the two-sphere. And it does have this form if you think about it. It's just that our stack of pancakes only has one pancake, okay? But it's a perfectly good covering map. And I would call this a degree 1 covering map because it is 1-to-1. Every point has one pre-image. Okay, in this picture, we had what looked like a degree 4 covering map. Okay, so the two-sphere is not very interesting from the point of view of covering space theory. If I pick a manifold with a bigger fundamental group, so here's the circle. The circle has fundamental group Z, depending on how many times a loop wraps around the circle. And Z has many more subgroups. The subgroups of Z are cyclic groups that depend on what the generating element is, right? So it has Z's worth of subgroups, which means that the cover, so the circle, should have a Z's worth of different possible covering spaces and covering maps. So here's again our degree 1 cover. We can always have a space map to itself, just like we did with the two spheres. So it's a circle mapping via the identity map to the circle, and it's 1-to-1. But we could also have, and this is another copy of the circle. I've just drawn it so it looks like it's knotted, like in Sarah's talk. And see, I drew it so it's going around twice. And so when I project down, I'll actually cover this bottom circle 2 times. It's 2 to 1. So this is a degree 2 covering map. And again, I could go around 3 times or any other finite number of times, and I find covering maps of the circle to itself. And there's something more interesting I can do, which I could consider a copy of the real line. So here, this is a copy of the real line. I've just drawn it as a helix, but it goes up and down for forever. And I've drawn it as a helix to suggest a way that I could project down to the circle, and I would have a countably infinite degree cover. So I'm going to use this symbol, omega 0, to mean countable infinity. Because I'm studying manifolds, this is the only kind of infinity we're going to see. We actually can't have an uncountable to 1 cover, because it violates, one of those weird properties of manifold. I'm sure we all remember what paracompact means, right? One of those things. Okay, but that's good, because otherwise I would get nervous. So that's a covering space. Covering spaces are very rigid. And by rigid, I mean, usually, if you pick 2 manifolds M and N, there is no covering map from M to N. We use covering spaces to do algebraic computations. If you learned about homotopy groups, we use covering spaces to determine the homotopy groups of manifolds. They give us a lot of information because of how rigid they are. So that's like a good perspective, but the bad perspective is it's very difficult to use covering spaces to generate interesting manifolds because they are so rigid. So a very common thing to do in the field is to loosen the definition slightly so that we're going to lose some of that algebraic information, but we're going to be able to make general constructions. Okay, so this is the idea of a branched cover. So a branched covering map is still going to be a map between manifolds of the same dimension, continuous map, and it's almost going to be a covering map. It's going to be a covering map outside of some sub-object, which I've called B for branch. And so this is a little bit weird because I've written an adjective here. I said codimension 2. I didn't tell you what B is. It's not exactly a submanifold. Like if you want to be really general, you use polyhedra. But all my examples are going to be so low dimension that it doesn't matter. B is going to be points, so we're good. So here's an example. I really didn't want to go after Sarah because her slides look so good, and now you're going to see what my slides look like. But this is a manifold, mapping to a manifold, complex plane, perfectly good. I wrote it as complex plane rather than real plane so that I could write a nice map. I'm going to consider the function where I input z and output z cubed. Okay, so this point here is supposed to represent 0. So under this map, 0 maps to 0, and it's the only thing that maps to 0, so it's 1 to 1 on 0. But everywhere else, it's actually 3 to 1, right? If I take these rays here at angles 0, 2 pi over 3, 4 pi over 3, when I apply z cubed, they all map to points on this ray at angle 0, okay? And then I also highlighted these sort of opposite green rays, which all map to this single opposite green ray here. So outside of 0, this is actually a 3 to 1 map. It's a 3 to 1 covering map. So this is a degree 3 cover except at that branch set, which is the single point 0. And see, that's codimension 2 in C. So this is a branched cover. And it's a simple example, but it's really like the example. This is always what branched covers look like locally. There just might be a more interesting global structure. Okay, so here's another example. It's the two-sphere again, and it's mapping to itself. I'm going to show a second picture to make it more clear what this means. But for now, what I want to imagine is that I have these 3 rays here that go from the North Pole to the South Pole. So I have 1 in the front, 2 in the back, and they're spaced equidistantly around the circle at angles like 2 pi over 3 between them. And again, I'm mapping to the two-sphere so that these rays all map to the same ray. So it's actually the same picture here. If I were looking down at the North Pole, this is exactly what I would see. A convenient way to think about this covering map is as a quotient map. I'm looking at a symmetry of my object. The two-sphere is symmetric under rotation that goes through 2 fixed points. And in this case, I'm going to choose to rotate 2 pi over 3. Of course, the two-sphere is very symmetric. I could choose a different angle. But I'm going to rotate 2 pi over 3. That fixes the circle setwise. And I'll take the quotient, identifying any 2 points where like one mapped to the other under this rotation. And again, I will get a two-sphere, but it's a 3 to 1 map. outside of these two fixed points, the North Pole is the only thing that goes to the North Pole, and the South Pole is the only thing that goes to the South Pole. So it's a 3-to-1 cover, and the branch set is those 2 points. Okay? Maybe I drew a more interesting example in the next slide. Did I? Yeah, I did. Great. So I made these. So here's a picture of a torus. So this is another example of a 2-dimensional manifold. When you first learn manifolds, first you learn the circle, and then you learn the 2-sphere, and then you learn the torus, and that's it. That's all of them. So this is the torus. And it has a symmetry as well. I could take this vertical axis that intersects the torus at 4 points, and I have to rotate angle pi, but if I do that, then it's symmetric again. So it's less symmetric than the 2-sphere, but still symmetric. And I could quotient by that rotation. And if I do that, you can see I've taken like the right half of this picture. That's what this is. I'll get a 2-sphere. And so this map, the quotient map, is 1-to-1 on these 4 points, but it's 2-to-1 everywhere else, because I quotiented rotating by pi halfway. Okay, so this is a degree 2 branched cover of the torus over the 2-sphere, and the branch set is 4 points. Okay, so far we have actually seen almost all of the oriented surfaces. Surfaces are totally classified by what's called their genus. So here I showed you a 2-sphere, which is genus 0, there's no holes. Then I showed you a torus, that's genus 1, it has 1 hole. In general, I could have a surface that has any number of holes. And that's it. Those are the only kinds of closed-oriented surfaces there are. And no matter how many holes I have here, I can arrange for it to be symmetric about this vertical rotation like before. So I have this axis, I rotate by pi, and I take the quotient, and I'll always get a 2-sphere. And the only thing that changes is how many times this axis intersects the surface. For every new hole, I get 2 new points of intersection. So this is a branched cover, degree 2, with this many branch points, 2g plus 2. Okay, so it's a perfectly good codimension 2 subset of the surface. Okay, so I want you to remember, if you haven't seen it before, the classification of surfaces. All there is like how many holes there are. Surfaces are really not very interesting. So just like be prepared for how uninteresting they are. Okay, so let me tell you a general theorem about branched covers, and then I'll pause for a question. So theorem, more than 100 years ago from Alexander, is that in fact every n-dimensional manifold is a branched cover over the n-sphere. So branched covers are super unrigid. We can get to any manifold we want, starting from the most basic manifold of that dimension. Okay, so before I continue, do you want to ask me a question about branched covers or surfaces or something? How are we feeling? Pudipang looks uncomfortable. It's okay. Yeah. Oh yeah, that's a great question. Okay, so he's asking like, what if I had rearranged my surface here to like not pass through all of the genus? So I could have, and again, I know it's like a slide, so I can't like edit it, right? But imagine that I had 2 more genus here, arranged symmetrically, like 1 on the left and 1 on the right. So the axis didn't go through all of them. When I take the quotient, I'll have 1 of them on this side will still be here in this picture. So I can get a perfectly good covering of this high genus surface over this would now be a genus 1 surface. Does that answer your question? Yeah, that's right. Yeah, I mean, any high genus surface can branch cover any lower genus surface by just carefully arranging how we want the different holes to intersect our line here. And we also have more choices where I was taking degree 2 covers specifically, but I could have rearranged the holes here to be symmetric about some rotation of a different order. There's really like a lot of structure here. Yeah, that's a good question. I think these are really interesting. This is one of the chapters, branched covers is one of the chapters in Rolfson's book, Knots and Links, which is my favorite introductory textbook to geometric topology, and this is my favorite chapter too, and like first-year grad students don't like it, but it's really fun. Okay, so these are branch coverings, and I want to compare this to what we just talked about with surfaces. Oh, and I'll point out these are closed, oriented, connected, because I'm always going to forget to say that, my bad. But let's compare to what we just saw. We saw that every 2 manifolds, so that's a surface, closed, oriented, connected, admits a degree 2 branched cover over the 2-sphere. And it's a slightly different statement. It's not just the 2-dimensional. If we look at it, there's this degree 2 thing here. So Alexander proved that n manifolds are branched covers over Sn, but he didn't say what the degree of the cover is, like how many preimages should a point have. Whereas for surfaces, we can really restrict that. It doesn't matter how complicated the surface is, we only need the map to be 2 to 1. Okay, so that seems really special, and it maybe is. So we can try to extend this to slightly higher dimensions. It's very easy to prove this for surfaces, and it becomes very hard when we go up in dimension. So in the 1970s, which when you compare that to Alexander, that's pretty recent, right, relatively. 1970s, Hilden and Montesinos showed something analogous for 3-dimensional manifolds. Every closed, oriented, connected 3-manifold admits a branched covering over S3 of specifically degree 3. Okay? So that's a slight improvement, just like surfaces. And then even more recently, 1995, Pergolini proved the same thing for 4-dimensional manifolds, but now they're all 4-fold branched covers over S4. So he can restrict the degree, unlike Alexander, who didn't do that. Okay, but it really caps out here. So I highlighted these 3s and 4s. This is an open question. Can you do this in higher dimension? Does every n manifold admit a degree n cover over Sn? Or at least, even if it's not specifically degree n, I'd be really happy if you told me they all admit degree 3n covers, or degree 1,000,000 times n covers, whatever that fixed number is. And this is completely unknown for all n greater than 4. I really thought about the 5-manifold case a lot that I'm embarrassed to admit. It's a lot I should have solved it, but I really don't know how to do it for 5 manifolds. And anything higher than 5, it's hard to believe that it exists sometimes. So I have no idea how to think about that. Okay. So I think this is a very interesting question. It's not what I'm going to do today because I don't know how to answer it. Instead, today I want to talk about removing the word closed. So I so far have been talking about closed-oriented connected manifolds. Connected is not very interesting to deal with. Disconnected manifolds are just, 2 connected manifolds put together, whatever. We just ignore that because it's annoying, but it's not harder. Oriented, it turns out unoriented manifolds are not really harder to study with branched coverings. It's just the theorem statements are slightly different, so I didn't want to put it in this talk. But orientability is not a big concern for technicality. But this closed is a big deal. And I'm going to say that a lot of the time when we state theorems, we say, closed manifolds. It's actually because it is making it easier. I sort of feel like the average manifold is not closed, but it's really hard to deal with non-compact things. So let me remind you, I'll put it in a second. I'll give you a theorem, and then I'll say what open is. But theorem, Pergolini-Judas, very recent-ish, 2016, oriented connected manifolds. They showed that if they have an open 4-dimensional manifold, then this manifold admits a degree something. We're going to have to parse this notation. Don't worry about it too much. But it admits a branched cover over R4. Okay, so there's a lot of weird things about this statement. The worst one is actually that this is a 4-manifold. Pergolini, I put one of his theorems just a few minutes ago. He's the one who proved that 4-manifolds all 4-fold cover S4. His research area is branched covers of 4-manifolds. I feel like that's not controversial. He has any paper you could think of that has to do with branched coverings in dimension 4. He's the author, or at least a co-author. One of my grad students is studying branched coverings, and the first thing I told him was you got to make sure Pergolini didn't already answer your question. And that was really touch and go. But I find it really unsettling that we have an answer here for 4-manifolds when there's actually nothing in the literature for 2- and 3-dimensional manifolds, which is the opposite of how that usually goes. 4 is bad, but Pergolini specifically studies 4, and this was sort of a consequence of his search into 4-dimensional manifolds. He understood the open case first. Very annoying. There's also this term ends here. We're going to get to that, but let's start with open. Let me remind you, when I say an open manifold, I just mean that it doesn't have boundary, but it is also not compact. So something like Rn doesn't have boundary and it's not compact. And that's our simplest possible open manifold. I'm going to give you a bunch more examples of open two-dimensional manifolds on the following slides. So, before I do that, any questions? Okay. Open surfaces are fun. So remember, we don't like surfaces. They're very boring, right? They're totally classified by genus, okay? Okay. So here are some open surfaces. The plane is a surface, and it's open. We just saw that one. The open cylinder, so like a cylinder, but I delete the boundary. Now it doesn't have boundary, and it's not compact. Perfect. This one's called the Loch Ness Monster. I didn't name it. That's not my fault. Do you know what the Loch Ness Monster is? It's like the thing in like the lake in Scotland where people take really blurry pictures and claim they saw it. But the blurry pictures always have these like spikes in a row. So it's, I don't know why someone would do this, but it kind of looks like, I don't know. Okay, this one's Jacob's ladder. That's honestly even worse, but I guess it kind of looks like a ladder. And both of these surfaces have infinite genus. The difference being that the Loch Ness Monster sort of starts somewhere and only goes off in one direction, whereas Jacob's ladder goes off in two different directions. Okay. So those are some surfaces, and that two different directions thing turns out to be like a huge headache. So an end of an open manifold is a class of unbounded rays, but informally, the way I want to think about ends of manifolds is it's one choice of how we could go out to infinity. So in these pictures I just showed you, the Loch Ness Monster, there's like only one way that I could go out to infinity. I could go out to the right. So the Loch Ness Monster has one end, and we're about to see it because I have a slide of things with one ends, and it's on there. Whereas Jacob's ladder, if I wanted to go off to infinity, I could go off to the left or to the right. So it actually has two different ends from each other. And that's why these two surfaces, Loch Ness and Jacob's ladder, have the same genus, but they are not homeomorphic to each other because they have a different number of ends. So it's like I thought so much about non-compact manifolds over the last year, and I kept having this feeling of like, I totally understand this. And it just kept getting worse and worse. Okay, so ends are really bad. We're going to see that. Okay. So here's some surfaces that have one end. The plane only has one end. This is a surface that's like, it's like a bowl, but I deleted the boundary. That only has one end because it's actually homeomorphic to the plane. Think about that one. This is a surface that has some finite genus, and then the genus stops, and we just go out to one direction. And this is that Loch Ness Monster, which actually has countably infinitely many genus. So it's definitely different from this one because they have different genus. Okay, these are actually all of the oriented surfaces with one end. One end is fine. I can make some surfaces that have more ends, but still a finite number. Like I could take the plane, but just delete a finite set of points. Like if I delete 2 points, now there's actually 3 ways to go off to infinity, because there's the one where it really looks like I'm going off to infinity, but I could also just get really close to one of these deleted points. I can redraw this surface more symmetrically as something like this. I have this Y shape, and all of these are not really boundaries. They just are, the boundaries are deleted or they go on for forever. So here you can really see that this has 3 different ends because I can choose whichever leg of the Y I want to go off on. Here's the cylinder again. I guess that one's good. It only has 2 ends. But then here's something like a cylinder, but I started putting genus like at every natural number point. So there's no genus on the left side, but on the right side there's always more and more genus. And then here's that Jacob's ladder where there's genus if I go left or right. So these 3 surfaces all have the same number of ends. They have 2 ends. The first one is definitely different from the others because it doesn't even have any genus. But these 2 surfaces, orange and purple, have the same genus, but they are still not homeomorphic to each other because this one in purple has 1 end with genus and 1 without, and this one has 2 ends that have genus. So those are actually different. You can't fix that with a homeomorphism. So it's not just number of ends, and it's not just genus. It's something else. Okay? So that's more, but still finitely many ends. And then it gets worse, because we could have infinitely many ends. So here's a surface with infinitely many ends. It's kind of like the cylinder, but at every integer, I sort of added like a new hole. Okay? So that has infinitely many ends. And then here's one where I started off with like something that only went to the right. and I added more holes at every natural number. These are not homeomorphic to each other. These both don't have genus, and they both have infinitely many ends. But the difference between these is if we tried to think about like which ends are similar to each other, like somehow on this orange surface, there's really two very special ends. There's the one where I always go left, and the one where I always go right. It turns out that when I count ends of a non-compact manifold, I'm actually not just counting, I'm building a space with topology on it. And so these two special ends, where I just go left and right, are limit points. Because I could compare them to starting somewhere and going off right really far, or going off right even further before I turn, and I could approximate it. Whereas in this red surface, I only have one special limit end. So they're actually different from each other. I could have one where I put genus in sort of one of these middle ends, or one where I put genus like the whole way left-right. These are also different from each other. Okay, and then it gets even worse. Like you sort of deal with this, and then actually you could have uncountably many ends. Because you could take like the plane minus a Cantor set. That's a perfectly good surface. Or you could take something where you have like start with a sphere and then choose, okay, I'm either going to go left, right. And then I'm going to choose, I'm either going to go left, right, I'm either going to go left, right. You continue on for forever. This also has uncountably many ends because these are homeomorphic, obviously. Great. I'm just kidding. I mean, they are homeomorphic, but you don't have to think that's obvious. Okay, but then I could take this surface and I could add some genus to it. And I could choose, I could put sort of one at every point, or I could put genus sort of like just in some. And these both have countably infinitely many genus and uncountably many ends, but they are not homeomorphic to each other. They're different. Okay, so surface is bad, actually. Good, great. Okay, so the theorem that I proved recently with Mark Hughes, who is a professor at BYU, Brigham Young University, and Sashka Kuchakova, who's a professor at Notre Dame University, both in the US, is that if you have a connected, orientable, open surface, then it is a branched cover over the plane, and we can bound the degree of the branched cover. It's either 2 times the specific number of ends of that surface, or it's countable infinity. So if you have a finite number of ends, then you can say exactly how many sheets you need in your cover, what's the degree. If you have an infinite number of ends, even if it's an uncountable infinite number of ends, then you still only need a countably infinite cover, which feels wrong, but it's right, though. It's okay. And we also resolved this, that's dimension 2, in dimension 3. So if you have an open 3 manifold, then you can find a branched cover over R3. And again, we can bound the degree of that cover, and it's either going to be 3 times the number of ends or countable infinity. Okay, so I'm going to sort of show you why the surface one is true, but do you want to ask a question first? That was kind of a lot with like all of that. That was bad. No? Non-compact surfaces, I think, were like popular for the last few years by people who do geometric group theory, but I don't know about it. But I feel like I saw them at a lot of talks, and I was like, why would anyone study that? And then I had to learn about them. They're fun, yeah. Oh, that's a great question. So in this theorem, the bound is sharp simply because there are certainly examples where I cannot replace the 2 with 1. There are specific manifolds where I can do better than 2 times the number of ends. So there are specific open surfaces where this is not sharp, but as a sort of general theorem statement, it's sharp. I'm actually going to pose an open question at the end about whether this 3 is sharp. There's something weird about the 3, but I'll point that out later. That's a really good question. Okay. So here's the proof idea. We're just going to do the surfaces one, because it's already bad, let's be honest. I didn't even give you any examples of open 3 manifolds, because like, I don't really know any. But so here's a typical trick for studying open manifolds. Open is bad, non-compact is bad. So what we usually do is describe our manifold using a compact exhaustion. That means that I'm going to write my manifold as an infinite, countably infinite union of ascending submanifolds, each of which are compact. So they like exhaust all the possibilities, okay? So here's a picture of a compact exhaustion. I'll do R3. It has a compact exhaustion where all of the EIs are B3s. So here's E1. It's like a small compact ball. And then like E2 is a bigger ball, and E3 is a bigger ball, and E4 is a bigger ball, and E5 is a bigger ball. And if I take the union of all of those balls, even though each one is compact, I'll get all of R3, right? Okay, so the point of this is that it feels like we can reduce our study of non-compact manifolds to compact manifolds because I only have to study each of these three balls. But it's still hard, the technical problem being that, let's say I want to do isotopy. When I do isotopy or like homotopy, right, it's always from time 0 to 1, a finite time. I have infinitely many three balls here. So if I told you, oh, do something to the first ball, and then to the second ball, and then to the third ball, I can't do something to all infinitely many in a finite amount of time. So you have to be really careful. We kept having a lot of arguments about the axiom of choice in this paper, which is you never want to be there. Yeah. Okay. So now I'm going to build a branched cover of a non-compact surface over the plane. So here's my plane. This is the analogous exhaustion by disks. So I have the smallest disk and then bigger disks going out. And this is one way of seeing that the plane is homeomorphic to that picture I drew before. So this is, again, an exhaustion by disks. I have this bottom, like, dark disk. And then sort of the next layer, it's just a taller disk that's overlapping. Okay? So this is another picture of the plane. And I'm going to imagine my non-compact surface mapping to this version of the plane. And I have an exhaustion of my non-compact surface, and I'm going to start off by like only dealing with the first piece of the exhaustion. Like this part is a big mystery, I'm not looking at it, but I know exactly what E1 is. And it's something. But whatever it is, I know it's a compact surface, and I'm very good at finding branched coverings of compact surfaces. So I can find a cover, see again, I drew this like axis, and I can like spin this E1 piece by pi, and it's symmetric. So if I take the quotient, I'll get a degree 2 cover over this lowest disk here in my plane. Okay. And then maybe I'm lucky, and I look at the next piece, E2, and it again has this nice property that there's only one like outgoing boundary on top. And in that case, I know exactly what to do. It doesn't matter how much genus it has. I can like extend this axis and have it go through the whole genus and have it cover this next piece. But then something bad happens. Like maybe I find a surface that has more outgoing boundaries. I guess that could happen. And I don't know how to deal with this because I can't have my axis here like just go through both of these. I don't even know what that would mean. I'm only rotating about lines. So what I have to do is redraw this Y-shaped piece. It's gonna look scary, but it's still a Y if we think about it. Okay, so it's okay, right? I don't know. So I just sort of grabbed part of it and pulled it down. And I also grabbed part of it on the right and pulled it down. And so what I want to imagine is that I already know this middle piece can cover something that looks like the plane. I already understood that. These new things that I created, they look exactly like my picture of R2, right? It's just like a bowl. And here it's just like a tall bowl. So each of these new pieces on the left and right can just map directly onto the part of the plane that I've seen so far. And now what I've done is make it so that there's this new axis of symmetry here. I have a bowl. This is secretly a bowl. This is a bowl. So I could take lines between them and be rotating around those lines. And this preserves the symmetry that each of these boundary components have an axis going through them, just like I did here. Okay. So I can continue this process iteratively and always extend my cover over the next piece of my exhaustion without ever changing the things that happened before. Okay, so like more bad things happen. Maybe I have more outgoing boundary components and I have to do this move again. But whatever, like it's just like an existence proof. I don't have to do an example. Great. Okay, so that's why I can get a branched cover over the plane. And I can also understand what was the degree of that cover. Because I started off with the degree 2 cover. And if I didn't add a new outgoing boundary, this was also degree 2 covering. And the bad thing that happened caused me to introduce these two new bowls, which each mapped exactly to this R2. which means that I added 2 new preimages than I had before. So instead of 2 preimages, now I have 4 preimages, okay? And so as I keep going, every time I add 1 more boundary here, I'm going to add 2 new sheets, 2 new degree. Was your hand up, or are you just thinking? No? Oh, sorry, okay. So we increase the degree by 2 for each end, which means that if we have a finite number of ends, then the degree is 2 times the number of ends. But the exhaustion is countable. I had countably many pieces. So if I'm adding a 2 each time, even if I do that infinitely many times, I just get countably infinite degree. So that's kind of weird, right? Like, what's 2 times uncountable infinity? But that's okay. Okay, so this is exactly the bound that I wanted to get. The degree of the cover is the minimum, 2 times the number of ends in countable infinity. The 3 manifolds proof is worse. We won't do that. That's okay. But the proof idea is very similar. The reason it's worse is you have to understand the 3 manifold proof in the compact case from the 1970s. One of my favorite theorems and proofs. It's really cool, but it's definitely more technical. Okay. So let me leave you with some open questions. So this is very similar to what you asked about before. These are the theorem statements that I put up. We have the older one of Pergolini-Judas, that 4 manifolds, open 4 manifolds, cover R4 with the degree, which I didn't really emphasize when I showed it because we hadn't talked about what ends was, but their statement is the degree is the minimum of countable infinity and 3 times the number of ends. And these are our 2 theorems. We had the 2 manifold and the 3 manifold theorem. And the degree of the cover was 2 times the number of ends, or countable infinity, for surfaces. And for 3 manifolds, it was 3 times the number of ends and countable infinity. So does anybody, who sees a problem here? What's like the bad thing on this page? Any suggestions? Something bad is here. I'm not saying wrong, nothing's, but just bad. It's a feeling. Putipang, what's bad, you know? I'm sorry. No? Okay. So, I'm sorry. So the bad thing is that in the Pergolini-Judas paper, they had 4 manifolds, but this is a degree 3 times ends cover. That's like so weird to me. In a different style of talk, I would have paused for like a really long time to complain about this, because Pergolini's theorem for closed 4 manifolds is that they are 4-fold covers of S4, and you really can't do better than that. If you know what the 4 torus is, it's a 4-fold cover of S4, and it is not a 3-fold cover of S4. Like 4 is the best you can do, branch covering. But somehow he gets 3 times the number of ends. So the 4 torus, if you delete a single point from it and make it non-compact, is a 3-fold cover, branched cover over R4. That's deeply unsettling to me. Whereas in our theorems, certainly we cannot improve this 2, because this definitely can't be a 1, because you couldn't have a non-compact surface with 1 end 1-fold cover the plane, because then it would just be the plane. It's a 1-to-1 map. So that's silly. But it's really not clear to me what to feel about this 3. It's like the 2 can't go down, but then here the 4 went down. So should this be a 3 or a 2? I just don't have a good feeling about it. Can we improve this 3? And by that, what I mean is it the case that a 3 manifold with k ends actually admits a degree 2k branched cover over R3? I have no idea. I have no idea how you would obstruct this. I have no idea how you would obstruct. I don't know. I don't know what to do with that. The obstructions for closed 3 manifolds being 2-fold branched covers over S3 do not apply, because the usual obstruction is to look at the cohomology of the manifold, the top degree. But because we're looking at non-compact manifolds, it kind of doesn't work like that. So that's a problem. And a very specific, interesting case of this is to consider contractible 3 manifolds and ask, do these admit degree 2 branched covers over R3? So this is one of the other bad things I learned about non-compact manifolds, which I was not very familiar with beforehand. There are many contractible 3 manifolds without boundary that are different from each other. They're not homeomorphic. And I told somebody that I didn't know this, and they were like, really? Because your PhD advisor sort of famously wrote papers about them. And I was like, oh, my bad. But that's okay, he doesn't know about it. So There are the regular examples of this behavior. There's a manifold called the Whitehead manifold. If you haven't heard about it, don't worry about it because I didn't draw a picture. But if you know what it is, that's awesome. But there's a named 3 manifold called the Whitehead manifold, which is contractible. And it is a degree 2 branched cover over R3. So I'm like, well, that's all I got. I don't know if this is true or not. I think that's really interesting. And then, of course, there's the analogous question in the compact case. Can you give a bound some degree that depends on n, so that any open n manifold admits a degree that cover over Rn, accounting for the number of n's, and then also like it could be infinite, okay? And so if we don't know how to do this for closed 5 manifolds, I really don't know how to do this for open 5 manifolds, but there might be some reason that it's easier in the open case, given that the bound on the degree got smaller. Here, I would sort of believe that it is easier. But I have not personally had an idea for how to do that. Okay. And then thank you. Yeah. Yeah, any questions? Yeah, Puripang? Oh, he asked, did Pergolini and Judas do the exhaustion technique? Actually, no. So Pergolini and Judas do something really different. Remember, they're studying branched covers of open 4 manifolds over R4. Their strategy is always to think of their 4 manifold as actually being the boundary of a 5 manifold. And they're looking at a ribbon surface contained in their 4 manifold and looking at what it bounds in the 5 manifold. And they do some very complicated diagrammatic moves to show that they can diagrammatically build their 4 manifold in this special way. It's something really specific to that dimension. If you have studied 4 manifolds, you might have seen something called Kirby calculus, which is how we build 4 manifolds using handles, and we have a nice diagrammatic theory of how to do it. Their moves are very specific to the way that we draw diagrams in that dimension. So we couldn't do what they did in dimension 3, but I also can't complain because, to be honest, dimension 3 is much easier. They just didn't feel like it. That's what my feeling is. But that's why we got a different bound, yeah. Yeah. Oh, that's a very perceptive question. He asked, do I need to control the exhaustion? Yes. The first step is a lemma about choosing the right kind of exhaustion. So I want it to be the case that when I look at the number of outgoing boundary components, that it never goes down. Like it can only go up. And I also want it to be that it never goes up unless it has to. So we have 2 lemmas about sort of like simplifying the exhaustion as much as possible. And that's not dimension dependent. It's just sort of, it's like a brute force kind of thing where like, oh, I have these 2 boundaries that aren't together. I'm going to take an arc that connects them and serger them together. But there is something technical with making sure we can do infinitely many things in finite time. It's like a parallel processing situation. It's kind of interesting to think about. Any other questions? Should I stop? Can we go? Yeah? Okay. Thank you very much for inviting me. Yeah.